Hey everyone, ready for the deep dive into a real head scratcher? We're tackling the monkey and the coconuts problem today.
Oh, yeah, classic.
5 sailors, a monkey, and a pile of coconuts they keep dividing up.
You think it's simple, but
It's anything but.
yeah,
Figuring out how many coconuts they started with? Well, let's just say it's tougher than it sounds.
deceptively tricky. That's math for you.
Right. And it's been around forever. Lewis Carroll even wrote about it in his diaries.
And in tons of old math textbooks.
Oh, and remember that Saturday Evening Post story?
The one where readers demanded the solution.
Practically rioted. But before we crack this coconut, can you explain the 2 versions of the problem? The original and the one Ben Ames Williams made famous.
Ah, good point. So the original, the really old one, that monkey gets a coconut, even in the very last division,
Yeah.
Williams, he changed it up. His version has the sailors splitting the pile evenly in the morning, no leftovers for the monkey.
Seems like a small change.
It is, but it makes the problem a whole lot harder to solve.
Gotcha. So, we've got our sailors, coconuts, a monkey who likes his share, and this little twist that really ramps up the difficulty.
Absolutely.
But how does all this connect to something called Diophantine analysis? That sounds pretty intimidating.
Haha, it does, doesn't it? But think of it like building with Legos, but you've got to use whole bricks, no cutting allowed.
I like that analogy.
So Diophantine analysis. We're looking for solutions to equations, but the answers have to be whole numbers.
So, no fractions of coconuts allowed.
Exactly. And in this coconut problem, the unknowns are, well, the original number of coconuts, right? And then how many each sailor gets in the final split.
Makes sense.
We've only got one equation for all the dividing and subtracting.
So that whole numbers only rule is key.
It is. It helps us narrow down the possibilities.
Like a missing puzzle piece, but you know it's got to fit a specific shape.
A whole number shape. You got it. Now, there are a bunch of ways to actually solve this this coconut puzzle.
Some more intimidating than others, I bet.
Maybe a little, but they each have their own charm. There's trial and error, of course.
The brute force method.
You could say that. It works with the original version, the one where the monkey gets a coconut at the very end.
Okay.
You just keep guessing numbers until you find one that, fits the pattern.
But for Williams's version.
Oh, you'd be guessing for ages.
So trial and error shows us how tricky this problem is.
It does.
But it's not really a practical solution for the one we're interested in. What about this sieve method? I've heard that one's kind of clever.
The sieve, it's all about narrowing things down strategically. Like sifting flour, to get rid of the lumps.
Okay. Luck?
We know that final number of coconuts each sailor gets, that's got to be divisible by 5, right?
Right.
So we start there and work backwards, keeping in mind the monkey's coconut, the repeated divisions. Anything that doesn't fit the divisibility rules, well, we toss it out.
So no more blind guessing.
Exactly. Logic and divisibility rules help us zero in.
Now, this blue coconuts approach, that one's got me curious. The name itself sounds, well, fun.
That one's all about making it visual, easier to wrap your head around. Imagine we add 4 extra coconuts, blue ones, to the original pile.
Blue coconuts, okay.
Each sailor, when they divide the pile, makes sure each blue coconut ends up in a different pile. They take the pile without the blue one, all combined back together.
So those blue ones, they're like placeholders.
Exactly. To make the divisions work out neatly. And since the whole pile with the blue coconuts was divided evenly 5 times, we know it had to be a multiple of 5 to the 5th power.
Okay.
Subtract those 4 blue coconuts, and boom, we have our original number.
Okay, I'm starting to see how these different approaches can really unlock this problem.
Each one sheds light on a different aspect.
But before we get too deep into the math weeds, I gotta admit, base 5 numbering and modulo congruence, those sound a little intimidating.
I can see why, but they're not as scary as they sound, I promise.
Let's hope so.
Take base 5. It might seem weird, but it makes perfect sense for this problem.
How so?
Every time those sailors divide the coconuts, it's all about groups of 5, right? So if we use a number system where each digit represents a power of 5, things get a lot simpler.
Instead of fighting the divisions by 5, we embrace it.
You got it. We start speaking the problem's language.
Pretty clever.
And modulo congruence. That helps us analyze the remainders after each division. Each sailor gives a coconut to the monkey, right?
Yeah.
So the remaining pile, it's always going to be 1 less than a multiple of 5.
I see. A pattern.
A pattern that modulo congruence can express mathematically. We're looking for a number that, after all that dividing by 5, always leaves a remainder of 4.
Okay, I think I'm starting to get it.
It helps us see the problem's structure and often a solution that wasn't obvious at first.
This is fascinating. We've gone from trial and error to imagining blue coconuts to different number systems and remainders, and I hear there's even more advanced stuff, like Diophantine equations.
Oh, yes, and the Euclidean algorithm.
Maybe those deserve a deep dive all their own.
They certainly do. Another time, perhaps.
But for now, I think we've got a good foundation for understanding this classic coconut problem.
Definitely a good starting point. And there's always more to explore.
There always is. But you know what I'm really curious about? A generalized solution. Like, is there a formula that works for any number of sailors? Not just 5.
Ah, now you're talking. That takes us even deeper into the heart of number theory.
I'm ready if you are.
We'll tackle that in part 2, so stay tuned.
Back again for more coconut craziness. I'm still trying to wrap my head around all the different ways to solve this problem.
It is a lot to take in.
But now I'm really hooked on this idea of a generalized solution. Can we actually find a formula that works for any number of sailors, not just 5?
We can. And that's where things get really interesting. It's like we've climbed to the top of that coconut tree, and now we see the whole mathematical landscape.
Ooh, I like that. But how do we even start making a formula that works for, an infinite number of sailors?
By looking for patterns, just like we did with the 5-sailor case, instead of using the specific number 5, we imagine we have, let's say, sailors.
For mystery sailors.
Sure. Each sailor does the same thing. Dividing into umpiles, giving one to the monkey, hiding their share, the whole routine.
So instead of those powers of 5 we talked about, now we're dealing with powers of them.
Exactly. And if we follow the same logic as the 5-sailor version, but swap M everywhere, we get something called a recurrence relation.
Recurrence relation, that sounds...
It basically describes how the number of coconuts changes after each sailor takes their turn.
Okay, so we've made it more general by using M instead of a fixed number. But how do we go from a recurrence relation, which is like a step-by-step recipe,
to an actual formula for the starting number of coconuts? Good question. It involves a bit of, careful unpacking of that relation, applying it times for all the sailors.
Sounds complicated.
It leads to a rather long expression, but thankfully it simplifies quite nicely.
Math magic to the rescue. So what does this simplified, generalized formula look like?
Well, once the dust settles, we get a Diophantine equation that connects the original number of coconuts, call it N, the number each sailor gets at the end, we can call that F, and our variable M, the number of sailors. It's actually a pretty elegant equation.
Diophantine equation, just like we talked about before. So even with our mystery M sailors, we still need whole number solutions. No coconut fractions.
Absolutely. And the beauty of this equation is that we can use some, let's say, clever number theory tools to find solutions for any value of M.
So we can plug in any number of sailors and find a solution. That's amazing.
It's like having a master key that unlocks, an infinite number of coconut puzzles.
Okay, my mind is officially blown. From a specific puzzle to a formula for any number of sailors, do you have an example of how this works in action?
Sure. Let's imagine just 3 sailors instead of 5. Our generalized equation will give us conditions that the solutions must meet. We can then use those to find the smallest possible starting pile for 3 sailors and, of course, the monkey.
So we're not limited to 5 anymore. We can solve this for a whole pirate crew.
Exactly.
But hold on, you mentioned clever number theory tools. Can you tell me more about those?
Yes. Remember modulo congruence? Looking at remainders. That's one tool that's super useful here. It helps pinpoint specific solutions that fit our equation.
Okay.
There's also something called Bezout's identity.
Bezout's identity, that sounds a little advanced.
Maybe a bit, but think of it like this. You have 2 gears, different sizes, and you want to know how many times each needs to turn before their teeth line up again.
Okay, I'm picturing it.
Bezout's identity helps us find that alignment between the original number of coconuts and the final shares. Make sure everything divides neatly.
So even though these tools sound complicated, they actually help us make sense of the problem.
They expose the underlying structure.
Like we're not just solving a puzzle, but deciphering a code.
I like that. And speaking of codes, did you know Diophantine equations and these number theory tools actually have uses in cryptography? Math isn't just an abstract game. It's all around us.
That's incredible. From sailors and coconuts to cryptography, who knew?
And the connections don't stop there. Remember we talked about generating functions?
Vaguely, yes.
We can even use those to find solutions to our coconut problem.
Wait, really? Generating functions? Those sound really high-level math.
They are powerful tools. Let's say the details for part 3, though. We've covered a lot already.
Good idea. My brain needs a break.
Mhm.
But you've definitely got me curious.
It is a lot to digest, but it's pretty amazing how far we've come from those 5 sailors and their monkey. We found hidden patterns, explored some powerful math tools, and even glimpsed the connections between seemingly unrelated areas of math.
And we're not done yet. I can't wait to dive into those generating functions and see what other secrets this coconut puzzle holds.
There's always more to uncover.
And we're back for the final part of our coconut odyssey. I'm still amazed by how much we've learned about this deceptively simple problem.
It really highlights the power of math to reveal hidden connections.
From Diophantine analysis to the sieve method, blue coconuts, even modular congruence. I feel like I've had a crash course in number theory.
And we've still got one more tool to explore, those generating functions.
Okay, bring on the generating functions. Remind me again, how do they fit into all this coconut business?
Imagine a line of coconuts, each one representing a possible solution to our problem, right?
Right.
A generating function. It's like a mathematical snapshot of that whole line.
Capturing the essence of the whole line.
You got it. It lets us encode all sorts of information about each coconut, its size, its position in the line, even how it relates to the other coconuts.
So we're not looking at each coconut individually anymore.
Nope, we're dealing with the whole line at once. And the best part, we can manipulate this expression, this generating function, to find out specific things about our coconut line. Well, for instance, we can use it to find the smallest possible number of coconuts that solves the problem. No more guessing and checking.
So generating functions are like a mathematical tool that lets us zoom in and out of our coconut line,
Yeah.
focusing on different aspects.
Exactly. We can even use them to explore different variations of the problem. Remember how we talked about what would happen if the monkey added coconuts to the pile instead of taking them away?
Yeah, I was wondering about that.
We can model that scenario with a slightly tweaked generating function.
Wow, so we can actually change the rules of the game and see what happens mathematically?
It's like a coconut simulator.
Yeah.
But seriously, generating functions give us this really powerful way to understand not just the classic monkey and the coconuts problem.
But a whole bunch of other problems, too.
Exactly. They're great for any problem where we're dealing with arrangements and selections of objects. Combinatorics, it's called.
I'm really starting to see how deep this problem goes. It
Yeah.
seems so simple at first.
It's a great example of how math can surprise you. You start with a puzzle about coconuts, and suddenly you're exploring all these interconnected ideas.
What's the main takeaway you hope our listeners get from this whole coconut adventure?
I'd say a sense of wonder about math, maybe? This monkey and the coconuts thing, it's a testament to the power of mathematical thinking.
It's not just about formulas and calculations.
It's about finding hidden patterns, making connections between things that seem totally unrelated.
It's about looking at the world in a new way.
Exactly. And who knows, maybe our listeners will be inspired to tackle some math puzzles of their own.
And if they ever find themselves stumped by a pile of fruit, just remember those coconuts. You never know what mathematical adventures are lurking out there.
There's always something new to discover.
Thanks for joining us on this deep dive, everyone. Until next time, keep those coconut brains working.